Thanks for attending the talk here. I will kind of give an overview of some of the work that we've been doing to try and use complicated wave interactions to detect very fine cracks. It's a challenge. In this case, we're using surface waves, so it's appropriate for the session where we're talking about near-surface characterization. We can't use this technology for deep inspection. I want to acknowledge my co-authors, Homin. He was my PhD student. Now he's a professor in Korea at Gachon University. And I also want to acknowledge Steve Feldman, who helped us a lot with the material side of this. But really, this work started many years before when I started thinking about, with the previous PhD student, how can we use this complicated wave interaction to find very small cracks? With normal ultrasound, you can't use very fine cracks. And I'm pleased to see that my PhD student is here. He's a professor now, Professor Homin. So this is work that is built on his work, and we've gone farther. In this case, the work was funded by the Department of Energy because they were interested in, my little laser pointer, detecting very fine cracks in nuclear power plant structures. And these cracks were motivated by the alkali-silica reaction. I won't go into detail here, but in summary, some aggregates are a little bit sensitive in high alkali, high pH environments. They go into solution, they create a gel, and they cause expansion. And this results over time in extensive damage in concrete. And here you see kind of a photograph of a kind of larger scale representation of this map cracking, as it's called. And when we zoom in, you see that actually there's lots of very fine cracks. Most of them go around aggregates or through the aggregates. Now, early on in this attack, we have no visual indication of this. It's very hard to see visually, but it's happening. We see these cracks distributed under the microscope. So the goal of this work that's been motivated for a long time is, can we use ultrasound, and in particular ultrasonic surface waves, to detect and characterize these fine crack network early on, before it's obvious by visual inspection. So in order to kind of motivate and help illustrate, here I show some simulation results. These are dynamic finite element. These are just simulations. But the idea is to give you an idea of how we go about it. It's a little bit complicated to be able to pull this information from the very complicated wave interaction that's happening. So what we have here is a finite element simulation. The top is undamaged concrete, but it has an array of aggregates in there which also scatter the data. And the bottom is the same model, but we, as you see here, we've kind of inserted a zone of near-surface cracks. Okay? So that's the difference between the two. And the cracks are just, in the finite element model, discontinuities. So a very rough simulation, but the purpose here is to illustrate what happens. So what I'll show at first is that we have a wave, a surface wave, which is shown by this kind of colored pulse that shows the energy of the wave. It's going to propagate across if the animation works. And you'll see that the surface wave is a coherent pulse. It's propagating across. It's losing a little bit of energy, but it's maintaining its packet. But you also see going backwards are some waves, and that's the scatter from the aggregates. That will always happen. That's disguising everything. This is undamaged material, but yet we have all of this scatter from the aggregates. How do we get around that? So we have a coherent forward propagating wave that's kind of hugging the surface, moving along. We have a backward propagating wave that's propagating at the same velocity, but going in a different direction. And then we have a mess of scatter all through the body. Okay? That's for perfect, pristine, defectless concrete. Now let's show the wave propagation, but now it runs into this batch of distributed tiny cracks. And so, show the same thing here. the wave propagates along, but then it'll hit the crack, and we have a lot of scatter in all directions. And I want you to look here. Here you see these pulsations that are not moving anywhere, non-propagating pulsations here. That is what we're trying to capture. Those non-propagating pulsations, which we did not see in the top. So we have a forward propagating wave. The energy gets kind of scattered here, and a lot of the energy is lost. We have a lot more backscatter, but we have these incoherent multiple scatterers, which look like non-moving pulsations. And kind of think of them as local vibrations, right? So we know at that point we have a local vibration. That's where the cracking is. How do we pull that out? Well, I'm going to go very quickly through this. But we can represent a time domain signal, time and space, time and space. We can take a Fourier transform in space, convert it to the wave number domain. We can take a Fourier transform in time, convert it to the frequency domain. And the time-space data now look like this. And in the wave number frequency domain, the forward propagating wave is kind of represented by this kind of energy packet here. And the backward propagating wave is this one. So they're like two packets of energy. Now, when we have the cracking, what we see is, now we have the energy is not just in the forward propagating and the backward propagating wave, but it's a big mess of energy at high and low wave number. Okay? So what the cracking does, it broadens the wave number of the scattered field. So how do we pull that out? And again, I'm going to go very quickly. So we have the time-space domain, and this requires collecting tons of data, right? This is actual data, collecting tons of it and just stacking it. So each one of these is a time domain signal in space, and we're stacking them. Here you see the forward propagating wavefront. Here you see all the backward propagating wavefronts. And here you see a mess in the cracked region. We convert it to the FK domain, and we have the forward, the backward, and the broadening, right? So if we're interested in this broadening content, all we have to do is take that domain and window out the forward and propagating mode. So this black means we just cut it out. So we're left with just this. But it's also interesting if we can window out the forward propagating one, because we know that the forward propagating one kind of dissipates over time, naturally, and then with the interaction of the cracks. So we take the whole domain, we take out the high wave number stuff, and then we window out just the forward propagating stuff, and we do an inverse transform to go back to this, and we do them separately. This is the forward propagating wave only. We don't see any backward propagating waves anymore because we've cut them out. And then this is the indication only from the broadening signal. So everywhere where you see in space kind of a high signal here, that means that pulsating thing. So that's the way we're able to pull out the crack signature from the overall signature. Okay, so we have this signal and this signal. And I'm sorry, there's just 2 more slides of this. So we plot out the kind of broadened signal, the incoherent multiple scattering, and we can do it over space, just like we had before. And we see that we have high signals where there are cracks, and there are no signals elsewhere. So just to remind you, this is the crack region. High signals here, no signals there. And then this is the forward propagating wave, right? So we have both of these, and what we do is we just divide one by the other to normalize them, and we have this normalized energy content, which is compensated for wave attenuation naturally. So the bottom line is, as we cross in space, when this number is big, we have a crack. And in time, it looks like that's represented by this pulsating, non-propagating activity. Okay? So this is the scattered energy in space. Where this number is big, we have cracks. Okay, how do we collect this data? Well, we use air-coupled ultrasound. We do that because by not touching the surface, we collect lots of data quickly. So we just send surface waves. Here's the sender. The surface waves are propagating here, and then this is a multi-element array here, and we just scan it, and we collect lots of data at every half millimeter or something like that. And we collect them across cross-section. So one scan here, and then we can move over and scan another one, and move over and scan another one, and then we have a 2D place. Am I out of time? Okay. Right. All right, and this is just some detail about our air-coupled receiver sensors. So just, again, to illustrate, here we'll do a scan over a concrete area. This is just a concrete surface, and we took a nail gun and just shot 4 places, so there's small localized cracking damage where the X's are. And here, we did it in the intact area and the scanned area. So here, this is actual data, so we can collect a lot of data and then reanimate it. Let's see if I can get out of this. And if it doesn't work, that is fine. So that's real surface wave propagation over an intact area. We see the coherent pulse across the scanned area. Okay, no problem. It's dissipating as it goes down. Of course, all waves dissipate as it propagates. Now look at this one. And what I want you to see is that we have non-moving pulsations everywhere where we have a defect. Right? Here's one. Here's another. Here's another one. Here's another one. Right? So that's just to kind of illustrate what we do. And then when we map in 2D that incoherent pulse, we see that in the intact region, we don't have any of them. And in the concrete region, we have indications exactly where the cracking is. And these are very small amounts of cracking. Ah, okay. Did you see the animations or not? Okay. Good. Thank you, Jordan. Okay, so can this work in the field? We were invited to NIST outside of Washington, D.C., Maryland. They had a very unique, they were studying ASR, and they had massive concrete blocks in controlled environments. There are 4 blocks here. You see a stepladder for scale comparison. 4 blocks, each with different levels of internal ASR in them. And this was in a controlled environment with a controlled mixture. We put our scan on top of these blocks and then scanned the top surfaces of all these blocks. And we went 3 times over a period of almost a year to see progressive damage in the blocks. The first 2 times we went there, we could see no damage in any of the blocks. By the 3rd time we got there, we started to see small, fine cracks in the reactive damage. And we just would put it on top and scan on the top surface. And you see here, after casting, we went at 4 months after casting, very early on, 8 months after casting, and a year after. Okay, and replicated the measurements. So there are 4 blocks. Mixed 4 is control. It has non-reactive aggregates in it and low alkali cement. The other 3 blocks had the same compositions with high alkali cement. The only difference is that they had different amounts of reactive aggregates. The coarse was a placitas, and the fine was a Jove sand. Mixture 3 had fully reactive aggregate. Mixture 2 had fully reactive coarse aggregate and half of the fine aggregate. Mixture 1 had fully coarse aggregate and none of the fine aggregate. Okay? So the thinking was that, okay, mixture 4 would have no expansion. 1 would be next, 2 would be next, and 3 would be the most. That was the thinking, right? And they did some expansion prisms. And you see here the 4x4 prisms did show that. So over 2 years, the non-reactive aggregates were in fact non-reactive, and there were no scatter. But we clearly have ASR expansion in the other ones, mix 1, mix 2, mix 3. However, in the 3x3 specimens, we have non-reactive, but mix 1 and mix 3 are higher, about the same, than mix 2. I want you to remember that, okay? So, how do we know what the actual ASR expansion is in these samples? Well, NIST did an amazing job. Each one of these were fully reinforced and fully strain gauged on the rebar inside. And so we had access to the strain gauges embedded in there, and we used that stress that was put on the rebar to say higher strains mean ASR expansion there. Okay? I just show you this is a elevation view, this is the top view in a cross section, and just to kind of, we're going to compare the response of certain strain gauges to our measurements at nearby that location. They're on the top surface, you see here, and the strain gauges that we'll look at are in this region, and strain gauges on the top, because we're measuring surface values and we're measuring the top surface. So first of all, when we map the entire top, so the color is that normalized damage number. You see that mix, and so a redder color, warmer color means more cracking. Interestingly, okay, mixture 4, control, very little cracking. 1 and 3, much more localized cracking. And here you see this is in space. We're able to localize where those cracks are. Mixture 2, less cracking. This is not what we expected. And what we can do is, so this is the 2D map. So for any 2D map, we can integrate over X and Y and get one number to give a damage value. Okay, so we're integrating all these numbers, combining them, and get one damage value. So I'll show you 2 results. One is we did a scan only nearby this strain gauge. Right? So a scan, a relatively small scan near this strain gauge. So I'll compare our output results, one number, to this strain gauge over the periods. First visit, second visit, third visit. So first of all, we see that this is the strain data. The expansion is going up with date. That's what we expect. The strain data were not measured at the first visit for R2, but interesting, it looks like mix 1 and mix 3 are higher than mix 2. Again, not what we expect. But we see the increase and we see the relative positions of mix 1 and mix 2. When we compare that to our number that's integrated, and here we have the control sample. The control sample did not have strain gauges in it. I don't know why, but they didn't. But here we see the same progression and the same order of the mix 1 and mix 3. Mix 2 being the lowest, but going to progression. This is just one localized area. If we do the same thing, but now we take a larger area, we take the average of these 3 strain gauges, we see again the same progression. Mix 1 and mix 3 about the same, mix 2 behind it. The lines indicate the extent of variation, so highly variable numbers, so we have to understand that. But we have the same trends with our scattered number. So our scattered number is matching very well with the results we see in one area, and a larger area average that. So in conclusion, we argue that this approach is able to find small cracks and locate them, very fine cracks, before we can ever see them. And we can, furthermore, determine the extent of the cracking, the severity of the cracking, and we can locate it. And we feel that the results here show that in real world, real ASR case, we can locate and characterize cracks in place, but it's near surface. I just want to acknowledge the funding agency, which is the Department of Energy, and then I really want to thank NIST for allowing us to come in and use those samples, because those were used for a completely different project that NIST had, and so we were able to do that. So thanks very much.